So let's go directly to the tricks of integration by parts. Trick number one. If you can't find the product of two things, let one of them be 1. Let dv be 1. You can't find the product of two things. And usually what happens when this kind of thing happens is you want to integrate a single expression. We can't find this as a product of two things, so let dv equals 1, which gives us v equals to x. 1 ds is precise, and then we have u is equivalent to ln of x, which means du is 1 over x dx. Integration by parts. We got this is x ln x minus the integral of u, which is x times 1 over x dx, which is equal to x ln x minus x plus c. So this is the first trick, which is not very commonly used, I think. It only works for things like arc sine or arc cos or genres. So I think trick number 2 is very useful. It's called getting the original integrand back. This usually happens when the integrand is consistent of only sine x, cosine x, and possibly some exponentials of x and negative x. So because the derivative of sine x is cos x, and the derivative of cosine x is negative sine x, when you integrate them twice, you'll get back the original expression. That's the idea of it. So if we have sine x, we integrate once, we get negative cos x. And then we integrate again, we get negative sine x. So these two come hand in hand with each other again. And I'm going to illustrate this to you using a proof question, actually. Integral of sine n x dx equals to negative 1 over n cos x sine n minus 1x plus n minus 1 over n integral of sine n minus 2x dx. This is called the sine reduction formula, where it allows you to integrate a high power of sine, decompose it to integrating a lower power of sine. You can repeatedly apply this formula and integrate it. So how are we going to go about doing this? Let I be equivalent to integral of sine nx dx. Then we integrate it once using integration by parts. It's equal to integrate sine n minus 1 x sine x dx. Right, integrating by parts, let u be equivalent to sine n minus 1x. du is going to be n minus 1 times sine n minus 2x cos x dx. dv is sine x. And then b is negative cos x. All right, so applying the integration by parts. This is going to get you uv, which is negative cos x sine n minus 1x minus the integral of negative cos x, so I put a plus sign right here, cos x times n minus 1 sine n minus 2x cos x. Cos squared x dx. And now what do we do? We have a cos squared x. This is equivalent to 1 minus sine squared. substituting that in, we'll get this entire expression in the front plus n minus 1 times the integral of sine n minus 2x minus integral of sine n x. And notice that this integral of sine n x dx was what we started with, right? Somewhere around over here. That this is I is equivalent to negative cos x sine n minus 1x plus n minus 1 brackets integral of sine n minus 2x minus I itself. So moving the I to one side, I get ni is equivalent to negative cos x sine n minus 1x plus n minus 1 integral of sine n minus 2x. Dividing both sides by n, and I finally get what I want. All right. So this is a classic example of using that, getting back the integrand. Does anyone have any questions about this? So I think this kind of proof is actually something that's very likely to show up in your midterm, because it uses integration of parts, involves trigonometric identities, and slightly difficult. So could definitely be something that's on your midterm. All right. We'll go back to this board over here. So I'll show you a past midterm question. Despite what I've illustrated in all these examples, I think the midterms actually have fairly easy questions. So this is the winter 2010 midterm question 2a. And it's to integrate from 0 to pi over 3 of theta secant squared theta d theta. All right, so clearly there's no substitution going on here. We can't express anything as a derivative of something else. So we have to integrate by parts because it's the product of theta and secant squared theta. So which one is the easily integrable one? Theta is both integrable and differentiable. So we can't do anything with that. Should we differentiate secant squared theta or integrate it? And the answer is to integrate because, and this is the part where it tests your trigonometric knowledge, where if you know that the derivative of tangent theta is secant squared theta, then this entire integral becomes problemless. It's very easy. This is going to be becoming let u equivalent to theta, du equals to 1 df theta, dv is equivalent to secant squared theta, and then v is the integral of that, which is just tangent of theta. All right, so this is now become an integral of u dv, which is uv minus 0 minus 0 pi over 3 v du, which is just equivalent to theta tangent theta from pi over 3, from 0 to pi over 3, minus v being tangent and du being 1, so integral of tangent theta, d theta. From this point on, you can either use the fact that the list of common trigonometric integrations that I gave you earlier, and realize that this tangent integral is just ln of secant of x, I believe. Right. Close, yeah, okay, negative. Still a little hand wavy about that one because remember what I wrote down is not negative. So
it's not negative.
Looks like that is
It's really weird because
yes. Yeah. Do you guys have a?
it's not negative.
Is it not negative?
Like I don't know. I remember looking at they moved the negative sign in somehow, but I forget how they did it.
Right. Okay. Maybe I'll visit that later on. But yeah, I think in the beginning I do remember that it being not negative, just ln secant x. But so realizing that, all we have to do is just substitute everything in. Thank you, Patrick, for putting that out. That it's just going to be, when it's 0, this entire expression is 0, so that becomes pi over 3 tangent of pi over 3 minus ln of secant of pi over 3 minus ln of secant of 0. Which eventually gives me, this is square root of 3. So square root of 3 pi over 3 minus, this is 1/2, which is going to be ln of 1/2. And this entire thing right here is going to be 1. So it's ln of 1, which is 0. That's that. So as you can see, it's very important to recognize that the integral of simple trigonometric functions, for example, integral of tangent theta right here is ln of the absolute value of secant x. It can save you a lot of time. All right. Okay. We're doing terms of schedule. Okay. I have to be faster now. Integration with partial fraction decomposition. By partial fraction. Okay, so when do we use integration by partial fraction? And usually is when the integrand is of the form a polynomial over another polynomial. And the idea is we want to decompose the huge rational function, the quotient, into a sum of smaller quotients, which are obviously easier to integrate. And the key is to factor the denominator polynomial. And I'll illustrate this. So it's when we're doing something like integral of px over qx, where px and qx are both polynomials. All right, case 1. Simplest case. The degree of p of x is smaller than q of x, and q of x is factorable. Two linear factors. Linear non-repeat factors. This is a simpler case where the degree of the numerator polynomial is smaller than the degree of the denominator polynomial. And the denominator polynomial can be factored into linear factors which are not repeating. An example of this is x plus 2 over x squared plus 7x plus 12. The first step of doing any partial fraction decomposition is to factor the denominator. And in this case, I'm not sure if you can see it or not, but it's x plus 5, sorry, x plus 3, x plus 4. Right? So what we want to do, we want to decompose x plus 2 over x plus 3, x plus 4 into something of the form a over x plus 3 plus b over x plus 4. And we can do so by matching the coefficients. This will give me, by finding the common denominator, that a x plus 4 plus b x plus 3 is equivalent to x plus 2 over the entire thing. All right, so all we got to do is just solve for the linear equation on top. So you can do so through matching the coefficients. Ax plus bx equals to 1x, 4a plus 3b equals to 2. But the way I prefer to do it is I want to do it by substituting different values, which are roots of the denominator polynomial. So in this case, I'm going to substitute values -4, because that will cancel out the a term and allows me to just directly evaluate the b term, and -3, because that will cancel out the b term and allow me to evaluate the a term. Sometimes that can save you a lot of time in terms of not having to solve for a system of 3 or maybe 4 different linear equations. So we have ax plus 4 plus b x plus 3 is equivalent to x plus 2. So the only values that will be used to you when you substitute it in are the roots, which are -4 and -3. Notice these are roots of the original denominator polynomial, which is x plus 3 and x plus 4. So this term will turn into, when you substitute in x equal to -4, we will simply get that 0 plus -1b is equivalent to -2, which results in b equals to 2. Similarly, we can substitute in x equals to -3, which will cancel out this term and allows us to do a equals to -1. And therefore, the integral, let's call it I, will now be -1 over x plus 3, I believe, dx, plus integral of 2 over x plus 4 dx. Which I trust you can integrate at this point using the logarithm functions. And don't forget the constant. Okay, so that was a very simple case of partial fraction decomposition. All right, so and this obviously does not only apply to polynomials where it's degree 1 on top and degree 2 on the bottom. It can be degree 2, degree 3, as long as the degree of the top is smaller than the degree of the bottom. Now obviously there are exceptions to this. What happens if the degree of the denominator is bigger than or equal to the degree of the numerator? Let's say, for example, degree, and I believe I said the top was p, is greater than or equal to the degree of the bottom is qs. What do we do in this situation? We use polynomial division. When we have a quotient of polynomials, we can divide it as if we're dividing numbers, integers. So recalling elementary school, I'm fairly certain you did something like this. Let's say it's 473 divided by 7. Right? We go on the 6 on here, we got 42, we got 13, plus 1, 7, 6. Now what does this mean? This means that 433 over 7 is equal to 61 and 6, 7. Right? All of a sudden back into arithmetic. So keep that example before we move on to polynomial division. Let's try something like x cubed plus 6x squared minus 4x plus 2 divided by x squared plus 4x plus 3. We're doing the exact same thing. We're going to write x here because that's the largest term we can put in here without making this larger than this entire expression. And then we're going to get x cubed plus 4x squared plus 3x. Doing the same subtractions, we're going to get 2x squared minus 7x plus 2. And then we're going to have another term right here, which is 2. It's going to give me 2x squared plus 8x plus 6. Canceling them out, 15x minus 4. And what does this mean? This means the exact same thing as before. This means that the quotient of x cubed plus 6x squared minus 4x plus 2 over x squared plus 4x plus 3 is equivalent to this number right here, x plus 2, plus the remainder right here, which is negative 15x plus minus 4 over x squared plus 4x plus 3. So what does this allow us to do? This will allow us to reduce the degree of the top polynomial, in this case being a huge third degree polynomial, to a sum of a polynomial term plus a quotient where the top polynomial has a lower degree than the bottom polynomial. Yeah?
Can you quickly wrap up partial fractions then?
Yep.
Yeah. I have a question for everyone. Do you want Simon to go over volumes and areas, or should we skip that in favor of differential equations? So everyone's fine with volumes and areas? Yeah. So.
Differential equation, no?
Oh, okay. So I think everyone's fine with volumes and areas. So it's just can we go to differential equations?
Okay, sure. I'll just quickly finish the last case.
Okay. Thank you.
Yeah, sorry, I'm just a little slow here. Lots of examples.
Tyler, like we want to do like the volume.
Oh, you want to do volumes? Okay, yeah. I guess, yeah, we want to do volumes.
Okay.
Okay.
Okay, so the rest of the cases are the exact same. Repeated linear factors. So suppose we have something like dot over x minus 8 to the power of n, x minus b, Then the partial fraction decomposition will be 1 over x minus a plus a1 over x minus a plus a2 over x minus a squared plus plus an over x minus a to the power of n plus b over x minus b dot. So basically, however many times this factor repeats in the denominator is however many factors we're going to have in the partial fraction decomposition. So I'm not going to illustrate that with an example anymore. I'm just going to go to case 4, which is irreducible quadratic factors. So this is, I'm just going to give one example here to illustrate it. This is from Winter 2010.